Hello, everyone. Welcome back. Hopefully, everyone had a relaxing short break over Thanksgiving. But we're going to get right back into chapter 13. And then hopefully, after chapter 13, we can jump into chapter 7, which will be, I believe, chemical reactions. So, chapter 6 homework is due on Tuesday, tomorrow at 11 p.m. While chapter 13's homework, I'm going to set it due tentatively for Friday at midnight. Just because we need to get through a few more chapters, and you should get through the homework on a set schedule. So don't fall too far behind. I encourage you to do the homework after the lectures for review and for practice, because that's necessary to do well on the final exam. So I have plans to announce the some extra credit opportunities, so stay tuned for that. One will be midterm corrections, as I announced in a previous email, and another will be an extra credit assignment relating chemistry to the real world. So that's a reflection assignment that I will announce with directions soon. So stay tuned for that. So let's just get right back into chapter 13. We were talking about structures of molecules. So we were talking about electron pair geometry. So previously we just drew the Lewis structures as these flat structures, but in reality, they actually have some 3D shape that we can actually visualize. And those shapes are dictated by common polyhedra that are known, for example, in shapes and geometry, stuff like that. So they are dictated by actual real world objects or shapes, and also by the arrangement of electrons around a central atom. The electron repulsion forces will always dictate what kind of structure is best for a given chemical formula. So let's talk about what these shapes look like. Okay, so electron pair geometry, we have three classifications that you're required to know. You'll learn more classifications, I believe, in probably Chem 2C, but you don't have to worry about that now. For our purposes, we only care about these three because they apply to non-metal atoms. You might encounter some compounds that have metals bonded to multiple other elements, but that is a later topic that we will not discuss here, but you will discuss in chemistry 2C. Okay, so see here, I have two bonds, so that means I have two bonding pair of electrons. So if I have two electron groups, they can be bonds, they can be lone pair of electrons, no matter what they are. So what I mean by groups is it doesn't matter if it's a single bond, triple bond, or double bond, that still counts as one group because it's bonded to one thing. So, or it's between one set of atoms, so one atom and another atom. So if I have two electron groups and nothing else, my bond angle is going to be 180 because that's the furthest the electron pairs can get apart. So 180, and we'll classify what the shape looks like, but you can kind of guess what it looks like. It looks like a line. So two groups, line, linear. So linear is this classification. B, when we have three electron groups, 1, 2, 3, the optimal angle is 120 degrees. So as we add more electron groups, we have to kind of compress the bonds because we need to make space for another electron or a part where there can be electron repulsion. So 120 degrees. And this is called trigonal because it looks like a triangle planar. So we call it planar because you see here, it's relatively flat. And remember, you need these three points here, these three bonds, they represent a plane. So a plane a physical plane. So if you recall from mathematics, a plane right here. So remember, 2 points are aligned, 3 or more for a plane. And then once we add another electron group, see here, the bond angles further compress to 109.5 degrees. And this is our first 3D model. So planar is flat, no 3D representation. Linear is just a line, no 3D representation. But tetrahedral now, we have another, we have a X direction, X, Y, then coming out here is the Z direction. So that's our first 3D shape. So this is what we call a tetrahedral shape because it looks like a tetrahedron or one of those shapes, or that shape we mentioned last time. So if you have 4 electron groups, you're going to be tetrahedral. You're going to adopt a tetrahedral shape. So it doesn't matter if it's bonds or lone pairs, it's going to be tetrahedral. Okay. So here is for 2 to 4 electron pairs. So we have 2 regions of electron density. Right here, 1, 2. So in here is the central atom, and here are the bonding orbitals for the terminal atoms. So regions of electron density or electron groups, we have 2. So we have a linear shape. So that's our geometry is linear. So bond angle 180. So I expect you to know all of these classifications for each of the electron pair geometries. So that's 2. Now, regions of electron density 3, so 3 balloons, 3 groups, 1, 2, 3, trigonal planar, 120 degrees. So you should be able to do this for any central atom. Okay. Now this is the tetrahedral shape, 4 regions of electron density, and the bond angle adopts as a 109.5 degrees. Okay. So that is tetrahedral. Those are the 3 shapes you need to know. So you'll get a lot of practice with this with the homework. So I encourage you to do the homework. Okay, so this table is meant to scare people. I will not worry about this table. So we'll talk about more examples, but you remember I said lone pairs can act as electron groups. So here, linear, we didn't have an example, but see here in trigonal planar, what if we have 2 bonds and 1 lone pair? So we call that, so the electron geometry will always be the same. It's either linear, trigonal planar, or tetrahedral. Okay, but the molecular geometry, what the shape of the molecule looks like, can be different. So electron pair geometry is just the classification of what the geometry is. Is it this class, or this class? And that's based on how many electron groups there are. But the molecular geometry depends on the shape of the molecule. So what does it look like? So if I still have 2 bonds, just 2 bonds, still linear, still looks like a line. If I have 3 bonds, still looks like a triangle, flat, trigonal planar. Now, if I have 2 electron bonds, so 2 groups are bonds, and 1 group is a lone pair, that means I still have a trigonal planar electron pair geometry, but my molecular shape is not going to be trigonal planar because I'm missing 1 bond, and it's substituted for a lone pair. So what we say is that the lone pair is going to compress the two other electron groups, the bonds, even further. So we call that bent. So when you ever have a lone pair and 2 other types of bonds to atoms, like in this example, sulfur dioxide, we call that bent. We'll talk about another bent molecule in a bit. Okay, so if we have tetrahedral, methane, still 4 bonds, that's still tetrahedral as both the molecular geometry and electron pair geometry. Now, if we substitute one of those bonds for a lone pair, we still have a tetrahedral electron pair geometry because we have 4 groups of electrons, electron domain, electron density, 1, 2, 3, 4. But 1 is just a lone pair. So when we have that, when we have a lone pair, we call it trigonal pyramidal. And it's trigonal pyramidal because that lone pair kind of acts as the apex of a pyramid. So that point on the pyramid, you could think of it as the lone pair. So when you have 3 bonds, one lone pair, still tetrahedral, four electron groups, still electron pair geometry of tetrahedral, but its shape is going to be not of a tetrahedron, but of a trigonal pyramidal. Trigonal because there's still three bonds, but it's not planar because it's not flat, and it has a lone pair. Okay, now we can substitute another bond for a lone pair. So now we have two lone pairs. So remember, we talked about this bent example here, a lone pair and two other bonds for the trigonal planar case. But once we have tetrahedral and we have two lone pairs, it's still two bonds as my other two electron groups. That can also be classified as angular or bent. So when you have either a combination of lone pair and two bonds or two bonding groups. So two bonding groups could be a single bond, both single bonds, or double bond and a single bond, doesn't matter. But whenever you have that combination of two bonds and lone pairs, that will always classify as bent or angular. And the electron pair geometry will always be different because you have to remember which one is tetrahedral, 4 groups, and which one is trigonal planar, 3 groups. Okay. Well, I know that was a lot of information, but the homework will guide you right through this. So do the homework for practice. Okay. So this is the classifications for molecular geometry. So when we have 4 electron pairs, we have a classification of tetrahedral. Now, what do the shapes look like? So we went over this on that chart, but here we go. For methane, methane is an example of tetrahedral, both in molecular geometry and electron pair geometry. All bonded electrons, so 4 bonding pairs of electrons, and no lone pairs. When we get to 1 lone pair, we get to ammonia. That's trigonal pyramidal. We still have 4 atoms. We have 4 atoms this time because we substitute one of those atoms for a lone pair. 3 bond pairs, 1 lone pair. Now, when we get to water, that's called bent or angular. I know it as bent or angular, whatever name suits better. So 3 atoms because we substitute another atom for a lone pair. Now we have 2 lone pairs and 2 bonding pairs. Okay. So we're going to talk about drawing wedge and dash diagrams. So you might be wondering, how do we represent these molecules in 3D space? So we use special types of bonds to do that, and I'm going to go over what type of bonds those are. Okay. So when the atom is in the plane of the paper, we just draw a single line. For example, like this. So these single lines denote that the bonds are on the same plane of the paper. So they have no 3D representation. So to denote the hydrogen coming out at you, we draw a wedged. We call it a wedge bond, like so. And then once and the hydrogens that are coming away from you, we draw a dash bond, the one I draw on the top here. That illustrates that the bond like this is going away from you, or towards the back of whatever's in your point of view. And then the wedge is the thing that's coming out at you to represent that 3D character. But this is just an example of what that is. So this is just a way of drawing 3D. I'm not sure. I don't think we'll see it. You might not see in the homework, but this is just an example how to draw a wedge and dash diagrams. And this will be very important when you talk about stereochemistry, which we will not talk here, but you'll talk about that in general chemistry. So it's good to know these dash and wedge bonds. So wedged Wedge is the shaded bond, comes at you. So if you were to build a model, you'll see that two hydrogen atoms won't be in the plane of the space. They'll be pointing at you, and one will be pointing away from you out into the distance. So that one in the distance is represented by this dash bond here. Okay. So here are steps to draw the molecular, to predict the molecular geometry. So draw the correct Lewis structure, count the regions of electrons, bonding and lone pairs, and determine the electron geometry and molecular geometry. So remember, if you have two regions, it can only be linear. Both geometries are linear. Three regions, you can either have all bonding pairs, that's trigonal planar, and electron pair geometry will be the same. Or if you have one lone pair in the mix, that's called angular or bent molecular geometry. And then four regions has the most classification. So you have all bonding pairs, tetrahedral, same with the electron pair geometry. 3 bonds and 1 bonding pair, that's going to be trigonal pyramidal. Then 2 bonding pairs and 2 lone pairs. I say bonding pairs, but you can think of bonding regions or bonds, angular or bent molecular geometry. So for these 3D, for tetrahedral ones at least, you can sketch the wedge and dash drawing that matches what you predicted in the molecular geometry. Okay, so for example, let's do this. Draw the, we're going to put this in practice now. Draw the wedge and dash diagram for nitrogen trichloride. So take some time to try and do this. Remember, first draw the Lewis structure, calculate the valence electrons, and then you could do the trick I taught you. Calculate the ideal number of electrons it wants, and subtract that. Subtract the actual number of valence electrons from that ideal number for each atom combined, and then divide the difference by 2, and you should get the total number of bonds expected in your structure. So let's draw this guy. Sorry, not this molecule. So nitrogen trichloride. So you can think of a nitrogen trichloride looks like an ammonia, except there's a chloride there. So you should have calculated the valence electrons and got this structure with lone pairs of the atoms. So it's actually not required to calculate the valence electrons, but it might help you predicting the structure. Here we omitted the lone pairs for clarity. See here that you should get the structure, but it wants you to draw the dash and wedge structure. So what you should do is make one bond planar, so one bond just a straight line to the chlorine atom, and the other 2 bonds will be dashed and wedged. So dashed for the other chlorine bond and wedged for the other chlorine bond to chlorine, and that's because we have 4 electron groups. It's not drawn, but this should have lone pairs on it. So you should have got a structure that matches this. And you see that lone pair occupies another bonding group. So it's four bonding groups. So electron pair geometry, tetrahedral with 1 lone pair of electrons. And so the molecular geometry will be trigonal. So the electron pair geometry is tetrahedral, right? So, but since we have 1 lone pair, it's like the ammonia example. So the actual molecular geometry, or the molecular geometry, will be trigonal pyramidal because there's 1 lone pair on this on the nitrogen atom. So we have tetrahedral electron pair, and then the molecular geometry is trigonal pyramidal. So this is our molecular geometry. Okay, let's move on. Okay. So I talked about multiple bonds. They still count as one electron group. So even though we have a double bond and we have a single bond here, they still count as two electron groups. So doesn't matter what kind of bond you have, they still count as one region of electrons. So that still counts as one group. So if anyone's ever confused about that, let me know. That's a very, very common mistake on exam and quizzes. Okay, remember, as predicted by our theory here, each region of electrons is distributed around the atom in such a way as to avoid electron repulsions or be furthest away from other electron groups, groups of electron density, because that's an unfavorable interaction. Okay, so let's try this exercise. Sketch the molecular. So let's sketch the molecular geometry of tetrafluorodiene. Okay, that's a typo. It should be tetrafluoroethylene. Sorry about that. So what you should do first is calculate the valence electrons, then do that formula, do that little calculation I told you to figure out how many bonds we should expect, and you should get something like this. So you should get a CC double bond in between the carbon atoms. So this is an example where you have two central atoms. It's both carbon atoms. It's symmetrical. And then the fluorine atoms will always, usually in Euler structures, fluorine, halogens, or hydrogen will always have one bond. So you can always be a safe bet with the halogens. So make sure all the electrons are accounted for, and you should get this structure. See here, each central atom has 3 electron pair groups. So look at the carbon here. We have 1, 2. Remember, the double bond still counts as one electron group, 3. So each carbon atom has 3 electron groups. So we classify it as trigonal planar. And since carbon has all 3 groups as bonded electrons and no lone pairs, we call the molecular geometry trigonal planar as well, and this structure is flat. It's flat, so it's like a sheet of paper. It's going to be flat with no 3D characteristics. Okay, so that is this example. So when it says sketch a wedge-and-dash diagram, that means if the molecule has 3D character or if it's applicable. So that, I think that kind of got cut off. Well, I apologize for that. So okay, so the wedge-and-dash diagram for in this example, they're the same, except in the Lewis diagram, you would draw the lone pairs like we have before. And when we talked about bonding for ionic compounds, we always drew the lone pairs. For a dash and wedge diagram, you don't have to do that. You just have to show the arrangement of atoms, or if there's a dash and wedge bond possible for the structure. In this case, it's not possible because it's flat and it has no 3D character. But as we saw in the previous exercise with nitrogen trichloride, we didn't draw the lone pairs. We just drew the bonds and the dash and wedge bonds to illustrate the 3D character of this molecule. Okay, so in this case, they'll be the same. So if I ever ask you a question, you could just do what this exercise did, and just draw the structure without the lone pairs, and you'll be right. Okay. All right, so now we're going to discuss polarity of molecules. So we kind of talked about polar covalent bonds last time and non-polar covalent bonds in chapter 6. It was I think it was chapter 6 or chapter 12. I forget, but I think it was chapter 12, because that's where we covered on the midterm exam. So So polarity has to do with a separation of charge in the molecule, and that's based on the distribution of electrons and bonds. So if you were to place these molecules up magnetic field, the more electronegative elements will align with the positive plate because they have more electrons, and the less electronegative elements will point towards the negative plate because now they have a deficiency of electrons, so they have a more partial positive charge. So polarity of molecules, they usually result from a uneven or asymmetrical distribution of the charge in the bond of the compound. Okay. So when do we know when something's polar or nonpolar? So you may have heard of stuff like methane, or carbon tetrachloride, which is a popular solvent, which historically is a solvent in the laboratory. So the conditions for nonpolarity or a molecule not being polar is you have the same atom bond. All the bonds of the atoms are the same. So we'll talk about what that means, but basically when all the bonds are the same, there's no competition for the dipole, because the dipole will always pull in the same direction on all four sides. For example, in methane, so the dipole will be oriented towards carbon, but since all the bonds are identical, there's really no separation of charge because it's symmetrical. So symmetrical molecules do not have dipole moments, just because the dipoles tend to cancel each other out. Methane, for example, won't have a dipole because the difference in polarity of carbon and hydrogen is so similar that there will not be a dipole. And plus, it's symmetrical. So think of symmetrical, no dipole, or not polar, so non-polar. Carbon tetrachloride, on the other hand, has more electronegative chlorine atom pulling the electrons in all directions on all four sides of the carbon atom, and those dipoles will cancel each other out. I don't expect you to know why they cancel each other out, but it has to do with vectors. So Era took math and he did like vector calculus. It's because of vectors. So vector subtraction, addition, but you don't need to know that. So when a molecules are not symmetrical around an axis or has no symmetrical properties, they result in polar molecules. For example, CH3, CH2, CO2, and CH3Cl. They all have they'll all have their own level of polarity in them, and that's because they're not symmetrical at all. So the molecules are not symmetrical. All the atoms are different, or at least different. So all the atoms around the central atom have to be the same to be symmetrical and have nonpolar character. When you don't have that, you result in a polar molecule. For example, these three examples on this slide. Okay. So here's an example of what we're talking about polarity. It results in a dipole moment. A dipole moment is basically you have a molecule that has two poles or two areas of different charge or charge separation. One area is negative and one area is positive. In this first example, CCl4, the positive charge is on the carbon and the negative charge is on the chlorine atoms. But however, since the pool of electrons is equal in all four directions, they cancel out, and so there's no net dipole or no net separation of charge. Therefore, no polarity in the molecule. So this is an example of nonpolar. Now, once we substitute one of those atoms for hydrogen, we see now that it's no longer fully symmetrical. So we're going to have, it's not symmetrical in the sense that the dipoles won't cancel out. So in this case, now we have the electrons being pulled by the chlorine atoms, and that force will add the vectors of those dipoles of the chlorine atom pulling electrons to itself, creating a dipole, and those dipoles will add to a net dipole that points towards the middle of the chlorine atoms. So that is an example of having a polar molecule. And as we get further down the line, that is there's always going to be a net dipole because it's no longer symmetrical. The dipoles don't cancel out. The dipoles cancel out in the first example because there were exactly two dipoles acting in opposite directions. But as we move down the line here, that's no longer the case. There's only one net dipole direction as you move towards the next compound. Methane is very similar in the case that there's no net dipole because the hydrogen and carbon have so similar electronegativities that we really can't classify that as as polar because their electronegativities are too similar, and all the atoms on methane are the same. So all the atoms around the central atom are the same. So there's no net dipole, and methane is not polar. So no net dipole moment there. And you see one way to also think of it is that the dipoles are acting in the same direction. For example, it'll come together. One will go this way towards the carbon atom, and one will go this way towards the carbon atom. So it's actually also cancel each other out because the dipoles, remember, vectors depend on value and direction. So wherever direction is coming from, it can also cancel out. So if it's not going in the same direction or one direction, it won't add. The vectors will cancel out. So this will be the same case here. You could think of it as methane, the vectors will cancel out because the dipoles are all the same and all in equal and opposite directions. Okay, hopefully I haven't lost anyone. That will also be reviewed in the homework, so I would do that. If this is not making sense, always come talk to me. Okay. So let's review no net dipole moment. Here, carbon dioxide, the oxygen is more electronegative. It will pull the electrons in opposite direction from the carbon atom. So the opposite directions, remember, when we have equal dipole moment and opposite directions, those vectors will add to zero. So there's be no dipole moment, so nonpolar molecule. All right, water, in this case, water, there's a lone pairs on oxygen right here. So that negative charge will attract the electrons from the partial positive of the hydrogen. So this arrow right here, that is a dipole moment. The partial positive end is at the butt of the arrow right here. And the head of the arrow shows the flow of electrons in the bond. The partial charges shows the flow of electrons in a covalent bond. So that partial negative charge is showing that oxygen is going to hog all the electron density. So in this case, our vectors will add, and you have a net dipole of pointing straight up to the oxygen. I do not expect you to draw that. I might expect you to draw maybe the dipole moment in a bond, but not the net dipole. Not the net dipole moment. I don't expect you to draw that. Okay, so that is water for triatomic molecules. Okay, so this is kind of just like a review slide about the differences of what we study in chemistry. Let me get a sip of water first. Okay, so two classes of chemistry, organic, inorganic. In Gen Chem, you will mostly cover inorganic chemistry, so chemistry that does not deal with really carbon atoms by itself. So organic chemistry, that's what I studied in grad school. It's the study of carbon compounds, or basically the compounds of life on this planet. So it has to do with the reaction of the carbon, how we manipulate certain molecules to form bigger molecules. And usually you see in organic chemistry, carbon, oxygen, hydrogen, and nitrogen. Basically, those main group elements that are non-metals. So that's essential for organic chemistry. For inorganic, we deal everything except hydrocarbons, which is basically compounds that contain hydrogen and carbon mainly, but can also contain oxygen. So all the chemical compounds except hydrocarbons and most of their derivatives. So the exceptions are that, carbonates, cyanides, which is a CN group, oxides of carbon, and other carbon-containing compounds. There are exceptions because although we talk about like sodium carbonate, there are exceptions because they are often classified as organic, and you see them in both when we teach organic chemistry and inorganic chemistry. So there's always some overlap between the two, so you can't completely separate them. But they're all hot areas of research in chemistry that bridge all the sciences: biology, physics, other interdisciplinary fields like biophysics, chemical biology, physical chemistry, stuff like that. So chemistry is kind of considered the central science. So you ever, in an involving field, it's good to have strengths in all three sciences, particularly in like biochemistry, where I think, some of the work or the job availability is moving towards, a bio-mediated approach to, drug design, tackling climate change, stuff like that. But anyway, that's the difference between organic and inorganic. Okay, so a hydrocarbon, I went over that. It's a compound made primarily of hydrogen and carbon atoms. So alkane, so methane, the thing we talked about, natural gas, that is an example of an alkane, and it only contains hydrogen and carbon atoms. And when we say saturated, that means there's no double or triple bonds. It's all single bonds. So all single CC or CH bonds. You can never have hydrogen in the middle between two other atoms. So hydrogen will always be a single bond to always carbon atoms. Okay. So alkane carbon atom is bonded to 4 other atoms in a tetrahedral structure, just like we saw for methane. So for example, these are all the classes of alkanes. Butane here, you may have butane, if you ever had lighters, if you use lighters, you like cook. If you're a smoker, I don't encourage it, but if you need to, in your lighters, there's a fuel that causes the combustion to help light stuff, and that's usually butane. Isobutane is an isomer of butane, and we talked about isomers. We just took one of these methyl groups and interchange it with the hydrogen here. So we put one hydrogen and put it on this carbon atom. Then that way we could break this CC bond and put it over here to form an isomer. So these two compounds will have the same molecular formula or chemical formula, but their skeletal structure is different. So they'll have different properties. So pentane is used as a solvent. It's a liquid. It smells like gasoline. It's a component of gasoline. So alkanes are also components of fuels, gasolines. I actually studied in my PhD work. I studied ways to convert, cellulose products or cellulose raw materials into value-added chemicals like fuels, monomers for polymers. So things that are of interest to industry, especially during these times, in which we are trying to phase away or move away from petroleum or oil-based products, given that the natural consequences that these processes have historically taken a toll on our planet. So we need to move away to more sustainable or renewable routes to reducing chemicals such as these, because historically these chemicals are produced from fracking or cracking, which is basically high temperature degradation of oil products to more simpler compounds, so like petroleum, natural gas. So that process requires thermal cracking or very high temperatures to break down the products in petroleum to get these compounds. That's why they call it like liquid gold, because it contains, even though oil is like this mixture of all these components and looks like dirt black, in it are these compounds that are very different in appearance, and you can extract that for money, 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 which is a big reason why oil companies are reluctant to move away from oil, coal, fossil fuels in general. Okay, anyway, enough of that tangent. Let's talk about. So we're just going to go basically over these things. I won't put much emphasis on it though, for like much emphasis, but be aware that it is on the homework, so you may be tested on it on the exam. Okay. So hydroxyl group is the OH group. So if you ever heard of ethanol, CH3, CH2, OH, that OH is the hydroxyl group, and it has important. It gives alcohols their properties because of this hydroxyl group. So related to the alcohol, ether, an ether compound, it has an oxygen in. It's a hydrocarbon, but it has an oxygen in its formula. So it's not like an alcohol because it doesn't have an OH group, but it has a COC linkage. And we'll talk about what these two look like. So here is methanol. Methanol, great organic solvent, but methanol. Methanol. Methanol is the simplest alcohol and industrially very important. And we won't get into the naming, but it's called methanol because it looks like methane, but one H is substituted with a hydroxy group. That's why we call it methanol. So that all signifies the hydroxy group. So here's methanol. We also have butanol, another important alcohol of the alcohol class, and C has a hydroxy group attached to the alkane portion, or the CH groups. And here is the alkane portion right here. So the chain length actually affects their properties. So methanol is actually more soluble in water than butanol because butanol has a longer alkane chain. Okay. Ethers are a little bit different. The oxygen is now bonded to two carbon groups and no hydrogen. For example, diethyl ether, the industrially most important ether for research in academia for organic chemistry. So it's a very popular solvent for many purposes. Then we have here methylphenyl ether, a different kind of ether where we have this ring here. This ring is called a phenyl group. By itself, we call it a benzene ring. You may have heard of benzene. Not a very great chemical. As you might have heard or know, most organic compounds are harmful to our body. That's why we always wear the proper PPE. Benzene especially because it's a known carcinogen, but not to scare you or anything. That should not stray away from doing research. I mean, if you take necessary precautions and be safe in the lab, you can carry out research just fine. I managed to survive more than 4 years in the lab. So that's because I was very diligent, very cautious, and always practice safe operating procedures, and always looked up a chemical before I used it because you never know what may happen. You may not know a certain hazard associated with it. So it's always important that when you're handling chemicals, it's not only that you're prepared, but you must kind of think about the hazards that may occur and think about the lab in general, and being safe. So it's always about being prepared, being safe, and giving the research process the respect and attention it deserves. But anyway, so that is ethers. So let's move on here. Okay, carboxylic acids. The most famous one is probably acetic acid, which is found in vinegar or some salad dressings that gives that kind of sour flavor to it. So carboxylic acids, they have this C double bond OH group. They end with IC, so like acetic acid. And most acetic acids, they are weak acids. They don't ionize completely in water. They ionize only slightly. So that's why you could probably, acetic acid, you could add acetic acid to your food because it only slightly ionizes, so that stinging or sour effect will only be minimal, and our bodies can take it. Now, if we were to try to digest a stronger acid, it will most likely damage us and can potentially cause us very deadly harm. So it can be deadly. So I mean, movies like to portray this, the acids in movies, but I try to try to avoid those movies. They're kind of exaggerating and give audiences a bad idea about what chemistry is about. But acids are no joke. So acids should always be handled with care. So I'm not sure how lab will work, next quarter for people entering Gen Chem, but hopefully you'll be able to, like do titrations or, handle acids. So you have experience if you ever want to think about doing a research position, join a research lab. Biology and chemistry, they often handle chemicals. Biology handles chemicals and specimens sometimes, if you're depending on what work you do. And if you're ever looking to a lab tech position, having this experience is necessary, especially for like clinical science, laboratory clinical science, in the professions, stuff like that. Any lab profession, this is essential that you're very comfortable handling reagents, instruments, and have a working knowledge of chemistry and what to do. Okay. So weak acids, they tend to only ionize in water. So that means they'll donate a proton, an H plus, and they'll have their conjugate base. But we didn't really talk about that, so don't worry too much about that right now. Okay, so these are carboxylic acids. Here's the simplest carboxylic acid, formic acid. Very important. So acetic acid and formic acid, very important in the industry for producing other chemicals. Their uses as solvents, very versatile uses. Formic acid also has applications, in I think biology sample preparation, and stuff like that. So the syntheses of these are very important for industry and how we get them, because they're produced on such large quantities every year around the world. Propanoic acid is the third simplest. So here we have 1 carbon, 2 carbons, now 3 carbons. Propanoic acid, another useful carboxylic acid. So these are examples of carboxylic acids. Okay. All right, that is end of chapter 13. We have about 30 minutes left, so we're going to jump right into chapter 7. Okay, so I'm going to go to chapter 7. So let's go to chapter 7 here. All right. So chapter 7, we're going to talk about chemical formula relationships. Okay. So we're going to talk about chemical formula relationships and how it relates to what we have been learning. Okay. So we're going to be talking about, so we didn't really talk about we did talk about atomic mass, but we didn't really talk about how it relates to what we can actually see. So we're going to be talking about stuff like molar mass. You may have heard that in high school, and moles, stoichiometry. So those are concepts that are very confusing. I talked to my peers, even people who took chemistry for that. That's one subject that people just did not get. So hopefully by taking this class, we can bridge that gap in understanding. Okay. So these are just learning objectives. This is what you should know by the end of after the lecture, after we talk about this chapter in full. Okay. So we're going to go back to basics here. So remember that when we write a formula, it means that, for example, if I have a formula of sodium nitrate, it indicates that I have one sodium atom and one nitrate anion. So the nitrate ion is composed of one nitrogen and 3 oxygen atoms. So a question I could ask is like, oh, based on this formula of sodium bicarbonate, I have blank H atoms, blank carbon atoms, blank sodium atoms, blank oxygen atoms. So remember that if we have a subscript if there's only one atom in the formula, we omit the subscript. One is implied because you can't have 0.5, 0 for a unit, formula unit. That wouldn't make sense. So that is how we break down the formula. Okay, so if I have ammonium carbonate, how many atoms of each element do I have? So let's remember that ammonium is NH4 plus. So to remember these these ions, I recommend making flashcards because it will help a lot with remembering the structures and the names of these things. So ammonium carbonate, remember carbonate is from carbonic acid. So remember carbonic acid has 2 hydrogens attached to it. So we remove the 2 hydrogens, we get carbonate. So we have CO3 2-. So these are the formulas for these ions. So carbonic acid, remember the ic changes to the 8 ions, so we remove the 2 H pluses, and then we get 2. So remember when we draw the formula, we need to balance the charges. Since we have no carbonate is 2- and NH4 plus is only +1, we need 2 of the ammonium ions to counter or to balance the negative charge of the carbonate ion. So when we write the formula, we're going to put our ammonium ion in parentheses, subscript 2, carbonate. So remember, when we're multiplying stuff into parentheses, it's just like what we did for learned in math. We multiply each thing in parentheses by 2 by the factor outside the parentheses. So we're going to multiply each element by 2. So we should get is 2 nitrogens, 8 hydrogens, because 4 times 2 is 8. 8 hydrogen atoms, 1 carbon atom. So remember, do not multiply the carbon by 2 because there's no subscript associated with it. And then oxygen, 3. So that is how we break down the atoms in the chemical formula. Okay. So hopefully that was okay. Hopefully we didn't get lost. So let's move on. Okay. So we need to talk about molecular mass and formula mass. So molecular mass is the average mass of the molecules of a compound, and usually represented by atomic mass units. And then a formula mass is expressed also in atomic mass units of one formula unit of a compound. So formula unit refers to ionic compounds. Molecular mass refers to like binary molecular compounds or molecular compounds in general. So for example, like carbon dioxide, that will be an example of molecular mass. So what we can do, all these masses, they're equal to the sum of all the atomic masses in a chemical formula. We call them averages because we're using the average mass on the periodic table. So equal to all the atomic masses, the sum of the atomic masses in a chemical formula, and we're going to go over what that means. Okay, for example, if I want carbon dioxide atom, or molecule, I could say that the sum of all the elements in that compound will give me my molecular or formula mass. So that's what we it's not the same as molar mass. So don't get that confused. Molecular mass is when we're talking about one compound, one molecule of the compound, or one formula unit, and that's when we use the atomic mass unit U. So it's the sum of two oxygen atoms here, and the one carbon atom, and we get a total of 44 atomic mass units, which is our molecular mass. Okay, so it's not the same as molar mass. We'll talk about that in a second. Okay, so let's calculate the formula mass of ammonium nitrate. So remember, formula mass, ionic compounds, molecular mass, molecular compounds, so stuff like carbon dioxide. So ammonium ion is NH4 plus. Remember, nitric acid is where we get nitrate from, or NO3 minus. Remember, nitric acid, I told you guys to remember those I think 6 or 7 acids that were the basis for all the other acids. So nitric is HNO3, take away the H. Now that means we have an H plus because it's an acid, and then NO3 minus because we removed one H, so we need to balance the charge. So since they are both of the same value but opposite charge, we simply combine these two compounds to write the formula. So NH4 and NO3. So let's calculate the formula mass. So we add all the atoms, the masses of all the atoms. If you have more than one atom of an element, you must multiply that by how many there are. So here, nitrogen, we take 2 times 14, get 28 atomic mass units. 4 hydrogens, so we times that the mass of hydrogen by 4. Then we have 3 oxygens, and we times that by 3. Okay, so remember sig figs. Sorry, that should be 48.00. Sorry about that. So remember, when we add, we look at how many decimal places are for each measurement. And in this case, both nitrogen and oxygen only have the significant digit out to the second decimal place. So our answer should only be out to the second decimal place. And see how we drew that line here? And our final answer is 80.05 U. So even though the masses on the periodic table are pretty accurate, we could only limit our answer to the least accurate one of the two. So when we're adding, that is what we do. We do not look at the total number of significant figures. We look at the decimal place. Although the least number of significant figures is also the same number of significant figures in this answer, but that is by coincidence. But so do not get those two rules mixed up. Okay. All right, we're going to talk now about a concept called the mole. And the mascot for the mole is the animal, the mole. So you may have seen this concept illustrated before in a cartoonish manner. So the definition of a mole is this: the amount of any substance that contains the same number of units, so the same number, of anything units as the number of atoms in 12 grams of carbon-12. Because carbon-12 has 12 grams. So we say that if we have 12 grams of carbon-12, we have 1 mole of the substance. So any amount that is equal to that contains the same number of, units of anything as 12 grams of carbon, we call that 1 mole. So 1 mole, it has been determined by Avogadro to be this humongous number 6.02 times 10 to the 23rd units of that substance. So if I'm talking about electrons, it can mean those electrons. It can mean ions. It can mean atoms. It can mean molecules. For example, how many, if I have 12 grams of carbon, it means I have 6.02 times 10 to the 23rd units, or in this case, atoms of carbon in my sample. So it can apply to molecules as well, formula unit as well. So we'll be using this number to represent the total amount of substance given our conversion from mass. So this is called Avogadro's number or Avogadro's constant. So it's a number that will pop up continuously throughout your chemical careers. I don't really use it in research, but it is the basis for stoichiometry. So stoichiometry, you do use all the time, especially if you work in a chemistry lab, and you have to weigh out material. But this is kind of the heart of stoichiometry right here. Avogadro's number relating mass to moles, and we use moles all the time. We do use moles all the time. Okay. So let's do an example. I know that might be kind of confusing, but think about it. So 1 mole equals Avogadro's number. So a sample of 0.25 mole ammonia, how many ammonia molecules is this? So remember, when we think about ammonia units, molecules, well, in this case, it would be molecules, ammonia units, which is molecules. So you're going to kind of link that back to Avogadro's number and say, oh, I must multiply the number of moles by Avogadro's number, because that's how many units I will get of ammonia molecules. Okay? So what we do here is, given mole ammonia, wanted molecules. So I know that my conversion, remember this is my conversion factor or my equivalency factor or expression, 1 mole equals 6.02 times 10 to the 23rd ammonia molecule. So now I just need to set up my fraction so the units cancel. So this can be a little bit tricky for some, but just think about, if I start out with moles, I must cancel out the moles by putting the mole on the bottom of my fraction, and then I will be multiplying by Avogadro's number to get molecules. So whenever you start with mole and end up with molecules or a formula or a unit for amount of anything, you should think, oh, my number should be way inexorbitantly larger. So way larger, like macroscopically larger than what I started with. So if I start out with mole and I'm converting to a unit or a unit using Avogadro's number, you should think to yourself, oh, I should be ending up with a very big number, or a very big, way bigger number than I started out with. And now you see here, moles cancel, and what we're left with is ammonia molecules. So you always want to end up with what you want here. Okay. Excuse me. So in the end, we end up with 1.505 10 to the 23rd ammonia molecules. So that's a lot of molecules. And it makes sense because we can't see these things. So when we weigh out a certain amount of it, there must be a lot of these molecules present in the sample. So this is how we do this type of calculation. Okay, now we're going to talk about molar mass. So molar mass is very different than molecular mass. Molar mass is when you measure out 1 mole of a substance. So in this case, we use a term or a unit we can actually physically measure out called grams. You can't measure out AMUs, that's way too small. So we use the molar mass to measure out stuff in measurable quantities, and that's how we do chemical reactions on the bench or in the lab. We express it using the molar mass. So don't get this confused with molecular mass or formula mass. Those two things are different. So it's kind of the same. It's the same process of how we calculated the formula and molecular mass. we just add up the atomic masses of each element in our compound, but at the end, we don't put U. Instead, we put gram per mole, because we're measuring out on the molar scale. So we put the weight in gram scale per mole. So molar mass is always gram per mole. So gram per mole. So if we had the atomic mass unit of carbon, so that's one carbon atom of carbon-12, that means it's 12 atomic mass units. So very, 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 very small in amount and in mass. Now the molar mass of carbon is very different. It's 1 mole of carbon atoms, so it'll be 12 grams per mole. So 12 grams is the molar mass per mole of carbon atoms. 12 AMU is the mass of 1 carbon atom if we were to say isolate it, but we can't measure out 1 carbon atom. That is impossible. Okay, so that is molar mass. Hopefully that was not too confusing. Just thinking, it relates to the mole, and that's how we measure out substances on a scale using the molar mass. But the calculation of the molar mass and the the molecular mass or atomic mass is the same process. Okay, let's calculate the mass of calcium fluoride. So we know calcium, so hopefully we can link back. Calcium is 2+ and fluoride is F-. So our formula should be 1 calcium atom to 2 fluoride anions, or sorry, calcium ion and 2 fluoride ions to write this formula unit. So calcium fluoride, CaF2. So now let's calculate its mass or its molar mass. So calcium is 40.08 grams and fluoride 19 times 2. So our sum is 78.08 grams per mole. Excuse me. So it's the same process for molar mass. We just add all the masses up, but in this case, our units at the end is gram per mole instead of U or atomic mass units. So molar mass, add these up all together. So yeah, so when you go, if you go, guys do labs, hopefully you do, you will measure this out, on a scale. Traditionally, that's how we did, in Gen Chem lab, but I'm not really sure how it will work. So, but I hope you guys have some meaningful lab experiences. Okay, so here's an example of 1 mole of compounds. So here's 1 mole of iron. See how much it is? It's a lot. So there must be a lot of atoms, molecules, stuff like that. See 1 mole of nitrogen, very, very huge in a balloon. 1 mole of mercury, sodium metal, copper 2 sulfate, nice blue color. I like that color a lot. See that blue color? Looks very nice. Mercury 2 oxide. See, so the mole represents an amount we can measure out and visually see macroscopically. So these is a very essential tool, not only tool, but way to practice chemistry on a practical scale. Okay, but usually in the lab, we work non-mole scale, usually sub-mole scale, below 1 mole, because weighing 1 mole of anything is a lot. Chemicals are expensive and they can lead to runaway reactions which you can't control. So you always need to control your variables, control your experiment, know what's going on, know what to expect, and know some other things, like have a contingency plan if things go wrong. So practicing any kind of science, you always need a very organized, detailed plan of action, and and other explanations to explain why your experiment failed and what you could do next to make your boss happy with your results. Okay, but anyway, let's move on here. Okay, so let's talk about this. You're carrying out a laboratory reaction that requires 0.0360 mole of barium chloride. So how many grams of compound do you measure out? So what we're given is, so take the time to do this exercise. It relates molar mass to moles. So we're given moles of barium chloride. So first we need to know what barium chloride looks like, the formula. But first, we want grams. So we're going to be using the molar mass to convert from moles to grams. So your conversion factor from moles to, units of something, like the amount of something, the total amount of like atoms or molecules, that's Avogadro's number. But you're converting from moles to mass or grams, you're going to use the molar mass. So grams. So barium chloride, barium is the same group as calcium, so Ba2 plus, so ionic compound. Formula unit must be Cl. Well, remember, Cl is the same group as fluorine, so it forms a -1 ion. So to counter the 2 plus charge, we need 2 chlorine atoms. So hopefully this is now kind of routine in your brain to writing these compounds, because you always have to know what the formula is. So you'll need to know how to write it. So I encourage you, if you're struggling with writing these, use flashcards. Okay, so that's the molar mass. So you would find a mass of barium and then a mass of the chlorine atoms and add them together. You should get this number, 137.3 grams per mole. Oh, sorry, no. Barium is 137. Chlorine is 35.45. My bad. So we add them twice, and our total is 208.2. Remember to always report the appropriate number of sig figs. This is addition, so you're looking at the decimal place, not necessarily the total number of sig figs. So that's our molar mass. So now we have moles. We need to get the grams. So we're going to multiply by the molar mass because it's grams per mole. Moles will be on the bottom. Those will cancel out. And now we're left with is grams at the end. So whenever you're starting with moles and end up with grams, you should always have a bigger number, because you're always multiplying. Well, I wouldn't say a bigger. In most cases, it should be a bigger value at the end, because you're multiplying by the molar mass and you're not dividing by anything. You should look at it that way. So moles times molar mass, moles cancel. Now we're left with grams. So barium chloride will be 7.5 grams barium chloride. And that's a lot. That's a lot of barium chloride. Think about what 1 mole would be. You have to weigh out 208 grams. That's a lot. And we usually don't do that. Okay. So hopefully we're comfortable now converting from moles to using Avogadro's number for amount or units, and now from moles to molar mass. And we could also go the other way around. Okay. So here is the conversion, like kind of path you want to be thinking about. If you're going from units to moles, you're going to be using Avogadro's constant to as your conversion factor. Now, if you're going from moles to grams, you're going to use the molar mass. And conversely, grams to mole, molar mass, you just divide by the molar mass. Mole to units, multiply by Avogadro's number. Units to mole, remember, units is that really large number, so your mole value should be much smaller. So you're going to divide by Avogadro's number to get to mole. So these are the links between the macroscopic and the particulate world. MM stands for molar mass, grams per mole. Na stands for Avogadro's number or constant. Okay. This is the so these are just the applications or the patterns of what we use this for. We could link through Avogadro's number a particulate quantity in a measured macroscopic quantity. So that refers to grams versus like units or atoms. Then specific applications, we can measure out these reagents using the mass in grams. So we calculate the moles, get our mass in grams. Okay. All right. So determine the mass in grams of 3.2 times 10 to the 24 molecules of sulfur tetrafluoride. Okay, so sulfur tetrafluoride. So sulfur tetrafluoride, let's figure out the chemical formula. So we're given 3.1024 molecules, and we want in grams. But instead of talking about the formula first, let's see what we want. Grams, right? So we start out with molecules. We need to get to grams. And the way we do that is we go from molecules, use Avogadro's number to get back to moles. Then from moles, use the molar mass of sulfur tetrafluoride to get the grams. So this whole process, when we combine the two, seems to confuse students the most. So hopefully by walking through this, you have better understanding, and doing the homework will reinforce that. So remember, let's calculate sulfur tetrafluoride. So molecular compounds, just as the name says, sulfur 1, tetrafluoride 4. So sulfur tetrafluoride is SF4. So we add the molar masses. Sulfur is 32, 19 for fluoride, fluorine, and we get for a total of 108.06 grams per mole. Okay, so now the long icky part, we take the moles of our SF. So moles could be so mole is an abbreviation for molecules in this case. So don't get confusion with the mole unit. They tend to have the same abbreviation. So we take our molecules. You see here, remember when we're going from molecules to moles, we must be going to a smaller number. So we divide by Avogadro's number. So divide by Avogadro's number to get mole, 1 mole of sulfur tetrafluoride. Then we use the molar mass to cancel out moles and end up with grams. So we're going to multiply. So when we're going from moles to grams, we're going to end up with a bigger number than what we probably started out with. So we're going to multiply by the molar mass. And that, in fact, what happens here. So in the end, we get 5.7 times 10 to the 2 grams sulfur tetrafluoride. And you see here, we use 2 sig figs because out of all our units, we only measured it out to 3.2 molecules of sulfur tetrafluoride. So we must limit our sig figs to 2 sig figs in our final answer right here. And also, when we calculate the molar mass, even though there's only 2 sig figs for the fluorine molar mass, we still don't use. We still want to calculate the molar mass. It actually should be 19.00. Sorry. So this should be 19.00. So that's why it ends up as being 2 decimal places in our molar mass. I'm sorry if that was confusing for some. Okay. All right, guys. So hopefully that was okay. Review this, start the homework. I know things are going to pick up quick, especially with finals coming up. But if you take it slow, I think you'll be able. I think it can be manageable. But if you do need help, please reach out. So we're going to stop there. We'll pick up on this part of the chapter next time. But remember, the homework, chapter 6, is due tomorrow at 11 p.m. And then this homework, I will start right away because I'm going to set the due date for Friday at midnight just to keep us on track. But anyway, guys, have a great start of the week, and I will see you next time. All right, bye.